this chapter, we will discuss the flowcharts and the graphical functions in Stateflow. The first point on our agenda are the flowcharts, and we discuss the difference between flowcharts and the state machines. The junctions and transitions are the only objects that we will be using in the flowcharts. The conditions and the actions are discussed as well. Handling interfaces and data. Then we'll talk about the predefined flow patterns and why it is so efficient to use those. And the graphical functions as a way of defining reusable functionality in Stateflow. Why shall we develop in Stateflow? Is Simulink not enough? In Stateflow, we can model, simulate, but also animate the Stateflow charts and state machines. This kind of animation is not possible in Simulink. This also allows much easier debugging. Why is the animation so important? Because we will be defining combinatorial and sequential logics, and it means that at some point of a signal, we will look at it and decide what to do. So the signal is a trigger, and so we can switch some specific path of a program. And it is possible in both flowcharts and state machines, but also in the reactive systems, combining the flowchart state machines in Stateflow with Simulink models. The reactive systems means that we have some kind of a back loop propagation. It's not an open loop system, but a closed loop system. It means the system can react to some specific internal states, and it can trigger some events, and it can react based on some kind of time condition. We can use external inputs for that. We can use supervisory controls, but also internal states. And Stateflow is supported for the code generation. And we will also see some code generation patterns with embedded coder, and you will decide by yourself whether the code generation is sufficient or not for your project. In my opinion, it's perfect. So the flowcharts are very simple graphical representations of program paths, and they are used for decision flows that do not require history. So there is no internal state. It means this kind of programs are re-entrant and reusable, because basically you do not need to save any variable in the global memory. If you want to save some kind of a state in a global memory, then you need to use the state machines. And here you see yet another object. So we have the transitions, we have the junctions, and now we have this state objects. We will discuss it in the next chapter. But for now, it is sufficient to understand that the flowcharts are stateless systems. So flowcharts shall be used for modeling combinatorial design. It means a stateless system based on some kind of combination of input signals. We can decide what kind of action can be triggered. Those might be input signals, those might also be some kind of local variables, and we will also see in the data dictionary of Stateflow how those interfaces will be defined. The inputs, the outputs, the locals. We will also be able to define those data types and other parameters. State machines shall be used for modeling sequential design. It means especially for reactive or supervisory systems that depend on history. So the internal state in the state machine will be defining the historical values. And so the next evaluation of the state machine will be based on what state the program was left in. In the flowcharts, they will be always having one single entry point, where in the state machines, they have the entry point at the state in which they were at the end of the last execution. So for the flow charts in Stateflow, the most important objects are the transitions and the junctions. And with these transitions and junctions, two objects, as you see, we can fully specify a flow chart. Those are the transitions, and this is the default transition at the beginning. We have the junctions, and be careful, those bubbles are not states. They are just junctions. So basically, you can also skip the junctions and have some kind of rounded transitions, but it is just very difficult to read. And so there are some preferred patterns also defined by different standards like MISRA SLSF, which you can use. And we have the last transition at the end. So basically, the good style is to use one default transition and terminating junction. Later, we will see some specific rules which define exactly this kind of patterns. Of course, this kind of a program is defining the empty if-else, where number 1 stands for first execution path and the number 2 for the second execution path. But as you see, there is no body of the program. So we need to define the conditions and we need to define the actions. How do you do that? For the definition of the condition, we're using the brackets. And so if you put some condition into the brackets, Stateflow will interpret it as a Stateflow condition. So in this example, we have the input in1, and the condition is that if the input in1 is bigger than param1, then the first action shall be triggered. It means the intermediate variable a shall be set to in1. Otherwise, if it is not true, so basically if in1 is smaller or equal to parameter 1, then the second transition will be taken, and so the second action will be executed. A is equal to parameter 1. As you see in this case, we have a clear if-else, and we will see that it is very easy to generate C code for this kind of a pattern, and it will look exactly the way you would expect. In the final transition, before the terminating junction, we will execute the last action in which we will set the output interface out1 to this local variable a, and this will be the final action. So basically, you understand very well what's the functionality of this flowchart. The good thing is that we have to learn only two objects. Those are the curly brackets for the actions and regular brackets for the conditions. As you see, you do not need to use or put some kind of an object from the Simulink or Stateflow library browser. Here you can just use regular text. And it reminds us very much on textual programming with C or MATLAB. So as a matter of fact, you can even choose whether you use the MATLAB syntax or C syntax. In our course, we are focusing on the automotive applications, and we will be using the C syntax because we will also generate the C code out of these functions to see how it actually looks like. So those are the conditions in the brackets, and those are the actions in the curly brackets. And here we also see the execution order. In the older versions of Stateflow, you could even change that execution order in the way you like to, but it resulted in a lot of misunderstanding during reviews. So there are some MISRA rules not to do that. In the first place, the transition with the conditional path shall be executed, and the other path, the second path, shall be unconditional. So this is actually a rule, and we will see those rules later. What about other objects that we see on the Stateflow pane? We see Simulink function and MATLAB function and truth table and history. And of course, you will see a lot of presentations on how powerful those are. But the interesting thing is that the standards are prohibiting it. From my experience, I can tell you that the reviews with this kind of objects are very, very difficult. And so the main reason why they are prohibited in production projects is that the reviews shall be very simple. The people shall understand right away what the programs are doing. And this will be also very helpful for yourself if you look into your software units 1 year from now, because you will actually forget everything that you have been doing, and you will need a lot of time to understand what's going on. You probably have seen that models that people would show you and you don't understand anything, and they would actually tell you that it is self-explaining. So it's actually not. So please don't use these prohibited features. There are even some special rules for prohibiting these objects, and that's why we'll not be looking into them. If you want to learn more about this functionality, you can watch the MathWorks Ramp Up Stateflow training. But as I said, they are prohibited in production, as well as these 2 blocks in the Stateflow library. In the younger releases, there are even more blocks, but please don't use that. So the chart block is the only one that we will be using. And why am I saying that something is prohibited? Because there are some rules defined by the Motor Industry Software Reliability Association, MISRA. They are called MISRA AC-SLSF, the modeling, design and style guidelines for the application of Simulink and Stateflow. Some of them are non-functional. They are just like style guidelines to understand models better during reviews. But many of those are really functional, and they will change the flow of your programs. So you shall be very careful. And in our tool, EverCheck, we implemented all of these rules, plus some other very important rules for safety-related applications in the automotive industry. These rules were also adopted by many other industries, and all safety-related projects that I have been coaching on are using this set of rules. It is very helpful for reviews and for the code generation. In these rules, you will see that the truth tables are prohibited. The boxes shall only contain the text. History junctions shall not be used. External C code shall not be used in Stateflow. You can embed external C code by using the legacy code function in Simulink. The MATLAB functions shall not be used, especially because you cannot define very exactly the way you want to generate code. And for the production projects, it's important. And also you cannot define very well the way of using the memory, which is again very important in production projects. Simulink functions shall not be used. It was a big feature of Stateflow in the last years that the Simulink functions were introduced to be used out of Stateflow. There might be some use cases for that, but they are really difficult to understand during reviews. And again, this is not really needed. So you can implement the same functionality with much more simple instruments, which are also very easy to understand and very easy to generate code for and very easy to verify. So the state transition tables shall not be used. Basically, state transition tables are like flowcharts in which you define the order of execution very well. But if you look into the academic understanding of the transition table, it will be different. And so there are some misconceptions about using that, and MISRA AC-SLSF is just prohibiting that. So transition actions are also prohibited because they introduce some kind of a misconception of how exactly and when exactly the action will be executed, especially if you are not using the debugger in Stateflow, but you're just watching some printout of your state machine or your state chart. And so MISRA ACSLSF is defining that the condition actions shall be used instead. And this is actually very easy to use also. So the state actions like during and exit actions shall not be used. Those are very compact actions, and we will see them in the next chapter on state machines, but they are again very difficult to understand for the people who are new to Stateflow. And see, the problem is that when the people look at the small state machine or flow chart, they feel like they understand what's going on, but then they have this kind of a during or exit action and they do not really understand the semantics of it. In the next chapter, we will switch on the debugger and go through these actions, and you will see how unintuitive it is with this kind of actions. So in every single review, you will need to explain exactly to those participants what's going on, because otherwise they will not understand the semantics if they are not experts on Stateflow. An event shall not be used except output events as function calls. If you remember the Stateflow demonstration, which is provided by the Stateflow product, it is called SFCAR. You will see all of this functionality included in that one single model. And we're actually using that for our demonstrations pretty often, just because it has all of this stuff which is prohibited. So that's for you. If you want to look into this kind of functionality, just go ahead and look at SFCAR demonstration. How do you handle the interfaces and data in Stateflow? In the background of Stateflow, data dictionary is called the Model Explorer. And you can click on that modeling pane and go to Model Explorer. And in that Model Explorer, you can really see what kind of objects you have inside of that specific chart. You will see the transitions, the local data, the inputs, the outputs, the parameters. You can define the data types, and you also can define all of the specific settings for that specific chart. The settings on the general pane fully defined by MISRA SLSF. And so it is also very easy to check by using some kind of static checker, and also to deterministically set those settings. So the inputs, the outputs, and the parameters are the most important objects for now that we will discuss. We can also define global data in the models and reference that global data, but the global data shall not be used in Stateflow because it is very difficult to understand what's going on, and also for the code generation it is not obvious. For safety-related functions, there are some special ways of how you deal with data for more safety and for the memory protection, and so global data is not the best way for your unit design. The parameters shall be defined as Simulink parameter objects. It is especially important because you can define the parameters for the complete project in one single file, say data dictionary or some kind of Excel file, and we will see some examples for that. All calibration data shall be passed as inputs to Stateflow. So inside of Stateflow, you can define parameters, and those parameters can be changed in the MATLAB workspace. But what can you do if you have production code? At the end, those calibration parameters are actually inputs to your units, and so they shall be defined as such. And if you use the Simulink parameter objects, you can also later define the way how code generation will be done. Because in the production project, you usually put the parameters in a specific module in the C code, and you also define where exactly they will be placed in the memory. You pre-specify with the linker where exactly these parts of the memory shall be allocated on your hardware and how exactly they will be referenced. All observed data shall be passed as outputs from Stateflow. So there are some very nice looking ways of watching the internal states in Stateflow. But if you think about debugging, verification on the model level, on the integration level, later on the C code level, also in the units and on the integration levels, you will always see that it is very difficult to do the more you go into the verification. Like you do the model in the loop first, then you go to the software in the loop where you embed your C code into the model, and then you go to the processor in the loop with your debugger, and again you use another set of tools, another set of compilers and debuggers, and you will see that if you do not care about it from the very beginning, it will be more and more difficult for later. So think about it from the very beginning, and we have to define it in a very simple way. So the name of a stateflow block, like input and output, should be the same as the corresponding signals. This is a general rule for Simulink and Stateflow. In this case, we see the in1 is the input, in1 is the name of the signal, and also the in1 is the name of the import for the chart. So this is the good way of doing that. It also will be very simple during reviews later on, so you actually make your life much easier for later. And this kind of rules can be supported by automatic checkers. So what about the junctions? Again, junctions, these bubbles that we have been talking about, which connect the transitions, they represent branches, not memory. And all junctions shall have an unconditional transition. So if you look at this one picture, first transition that will be executed that goes out of the orange junction, the first condition in 1 is bigger than parameter 1. This is the conditional transition that will be executed first, and then the second transition does not have any condition. It does have only one action. It might have more actions, but it does not have any condition, and that's why it is called unconditional transition, and this is the second which will be executed. If you would turn it around and set 1 at the unconditional transition, then the condition will never examine, and that will lead to the wrong code, right? So this kind of context can be overseen very easily in your projects. I've seen that before. It was a big disaster. You would be debugging for a lot of time until you would see that there is the wrong order of transition execution. This will be checked automatically now. This is a very helpful thing. The junction shall have only one conditional transition, and junction shall have a default execution order. It means that the conditional transition shall be tested prior to unconditional transitions. So what about the terminating junction? So this is the last junction in the execution of the flowchart. In the flowchart, there shall be only one terminating junction. You will see a lot of examples out there where people will present some kind of charts with different terminating junctions. They will also use transition actions and back propagation. This is very dangerous in production projects because, as I said, not everybody understands this kind of semantics, and people cannot review that effectively. The terminating junction shall have only one incoming transition. The cool thing about this is also that during debugging, your flowcharts will be highlighted and the path is very well seen then, and it helps a lot to understand how exactly your path will be chosen. Very, very cool thing. We will see that as soon as we go to our demo. The incoming transitions of the terminating junction shall be unconditional. You might have some kind of an action on that transition, but there shall not be any condition, because if the condition is not true, then the terminating junction will automatically move to another place, and again, people will not understand what you're doing. The terminating junction shall be lowest junction of the flowchart. So your flow should be from the top to the bottom and from the left to the right. The transitions shall be exactly straight lines, and they shall begin with a junction and they shall end in a junction. The only exception would be the initial condition, which does not have a starting junction. Transitions shall not cross other objects. Of course, there are some very complex state machines in which you need to cross the object, but if something like that happens, there might be a chance that you can simplify that kind of a state chart. The transitions shall not cross state boundaries, and here again there are some exclusions, like in the superstate semantics. The superstate is a state which has some internal states. There might be many hierarchies in a state. You can see on this picture that there are two superstates and they have some internal states, and you can really connect with one transition to internal states which will be crossing the boundaries of the superstates. So there is no other way of doing that, and that's why it is an exclusion. But you should be, again, very careful with this kind of semantics. The transition labels shall be visually associated with the transitions. So labels shall be placed to the right of the vertical transitions and to the top of the horizontal transitions. The labels are not the comments, but the actually executed parts of the programs. This is the program flow. Transition labels might be conditions or condition actions. This is a very good way of associating them. In the older versions of Stateflow, it was possible to move these transition labels somewhere, and the people would really misunderstand what's going on. What about the conditions? Conditions in the brackets. Up to 3 logical subconditions may be described on one line. If you put more, it is difficult to read. A new text line shall be used for each logical subcondition if there are more than 3. Parentheses shall explicitly describe priorities of different types of Boolean operations. And in multiple conditions, the logical operator and or shall be placed at the start of a new line. What about the actions? As we said on the previous slides, the transition actions are not allowed by MISRA SLSF because they are difficult to understand for the reviewers. So we can use the condition actions, and they do exactly what we expect them to do. So if the condition is true, then this condition action will be executed. Use a new line for each single action. The semantics of Stateflow allows putting everything on one single line, but this is not a good practice. Use a new line for condition action braces. Each Stateflow action shall be closed by a semicolon. Otherwise, the output will be put into the MATLAB command window, and for debugging reasons, that might be okay. But for the execution of big Simulink models, it will be not so nice because it takes a lot of time. So it actually slows down the simulation dramatically. The conditions and actions shall not appear on the same transition. So you should always separate the conditions and the actions. I usually use the horizontal line for the conditions and the vertical lines for the actions. Stateflow data. The identifiers of all objects shall be unique in Simulink and Stateflow, including local data, events, and states. Stateflow data shall have unique identifiers across a chart. Stateflow data shall not be grouped. It means you shall not use bus signals. Why is that? Because very complex structures of data will be passed to the Stateflow, and during review, you do not really know what that specific Stateflow unit is good for. Some developers will argue that the Stateflow charts and the models look cleaner, but yes, they do look cleaner, only the complexity is hidden and masked. And this is not good for reviews and not good for conquering the complexity. You should try to simplify your software units instead of hiding that complexity. The usage of named data instead of literals, like magic numbers, like imagine you have just number 42, is required. Instead of 42, you should use the parameter or constant. The only exception from this rule is the usage of literals 0 and 1 in counters and relational operations. MATLAB variables true and false are recommended for Boolean data. Stateflow data shall have explicit definition of data types, dimensions, and ranges. And typecasting for literals is not allowed. You should use the constants and define the unit type instead. What is about the mathematical operations? In Stateflow, the semantics allows algebraic, relational, logical, bitwise, unary operations and assignments, like y is equal to u1. This is the assignment. Stateflow conditions shall contain only logical and relational operators, no calculations. If you want to have a calculation, you should introduce a local variable instead, calculate your stuff, and then use that local variable in the condition. Why is it so important? Because during debugging, you will only see the value of that local variable, and otherwise you would need to calculate it in your head or somewhere on the piece of paper. So it's actually simplifying the job during debugging and development, and it's also not bad for the code generation because the compilers will actually optimize that code in the way which is the best for this specific hardware. Individual stateflow actions shall contain only one type of operator, like only addition or only subtraction. Now, if you want to introduce very complex mathematical operations, there might be a chance that you want to pre-calculate it in Simulink. So basically, it's about your architecture. Stateflow is not very good for calculations. It's not defined for that kind of modeling. Simulink is suited for mathematical operations. Stateflow is good for conditional operations, for reactive modeling. If you have a lot of calculations, there might be a chance that you should define all of that in Simulink. It might be easier for debugging. So Simulink and Stateflow are not competitors. There are some things that are beautifully modeled in Simulink and some other things that are better suited for Stateflow. So be careful with choosing which tool you're using. C library functions and MATLAB functions besides typecasting shall not be used in Stateflow. If you introduce some C library function, then you might do it by using the legacy code function. If you have MATLAB functions, then you probably need to specify it in a different way, and basically you don't want to introduce MATLAB in your production code because it is difficult to control the way the code generation will be done. But of course, there are always some kind of exceptions. And Stateflow option enable C-like bit operations shall be switched on. As you see, most of these rules can also be checked automatically by automatic checkers. What about comments? We can use the C-like comments in Stateflow. They can be drawn at the beginning of each label. You can separate those by new line from the rest, and they will be used for the code generation, and you will see exactly this kind of comments in your generated code. This is the way to put descriptions which you will need in the C code to find the specific passages and algorithms. We use that comments for requirements linking and for specific descriptions, which we will also see later in the generated code. You should use the normal 100% zoom factor of Stateflow for Windows. It helps with the printout of the Stateflow systems for reviews and for documentation. In some cases, that Stateflow charts and state machines are so big that they cannot be displayed well on one monitor. It usually means that your Stateflow functionality is too complex for that specific kind of software architecture, and you need to decompose your Stateflow charts and state machines. You might use some subsystems, some subcharts, they are called in Stateflow, or you can even divide the Stateflow functionality into multiple charts. It might have some influence on the code generation, but in the most cases, you shall be looking at the reviewability of your systems in the first place and not thinking about some kind of optimizing the C code in the later phase. You can use the preset factory color and style scheme for objects. It is not advised to recolor your Stateflow charts. You can use Arial standard 10-point font for text, except title. The title will be bigger, and again, those are automatic checks that we will provide. All text of the state label shall be within the state boundary. And there are some extra chart properties also predefined by the MISRA SLSF rules, which we will explain here, like the update method should be inherited, then enable CBit operation shall be set on, the support variable size array shall be set off, the saturate on integer overflow shall be switched off, enable super step semantics off, execute or enter chart at initialization shall be off, use strong data typing with Simulink IO shall be on. It means your Stateflow chart is well synchronized with Simulink and using same data. Action language shall be C and state machine type shall be classic. A user specified state transition execution order shall be off. You want to have the default transition order. The initialize outputs every time chart wakes up shall be off. As you see, all of that can be set deterministically, and we have special checks for that. Now let's look at the predefined flow patterns. Of course, you can define your modeling guidelines, but the better way is to use the MISRA SLSF guidelines, and they are also introduced here in the Stateflow patterns. By default, you might go to the add pattern in chart and add your if else, or whatsoever loops in the way that are well understood by different people, because they are well defined and used exactly in the same way. You can reuse some custom flow patterns in the graphical functions. The graphical function is basically a flowchart which is put in a specific graphical function box, and you can pass the imports to and get the output out of that function. You can imagine that it's like a function in the C code, and now as it is a function explicitly, you can reuse it just by calling that kind of a function all around your model, because it is visible globally to all other charts. This is a kind of reusability that you can integrate in your code, and defining libraries like that might be helpful, and it might make your flowcharts compact. They look simpler, but there is also a problem with that graphical function, that if you are now debugging, you need to open several windows. You do not see on one level of integration what's actually is going on. So basically you will need to open that graphical function and debug in that function, and you need to change the context and the windows. So I was very keen on using that in my previous designs. Later on, with maintenance of my systems, with debugging of that systems, I learned that it is difficult for reviews, and I'm not using this kind of a pattern anymore. I'm trying to use the flowcharts embedded in the functionality where I need that. The only advantage of this is that you will use one piece of ROM, but ROM is not such a big deal for us. In the automotive industry, we have enough, and it introduces an extra level of complexity during development and reviews, and so I'm not using that anymore. With the graphical functions, if you decide to use that, you should be careful with the return value from that graphical function. It shall be set in only one place, and so you need to introduce some local variables if you have some intermediate calculation. The return value from a graphical function shall not be used directly in a comparison operation. So you need to pass it to another variable first and then use it. As a summary for this chapter, we discussed the flowcharts versus state machines. Flowcharts are stateless systems. They use only two objects, junctions and transitions. On the transitions, we can define the conditions, and based on that condition, we can execute different actions. We learned the Model Explorer for handling interfaces and data. And we talked about the predefined flow patterns for conditions, loops, and other programming techniques. At the end, we introduced the graphical functions as reusable functions, which can be called globally in the complete model. And in the next chapter, we will dive into the state machines. That was the theory of flowcharts, and now we have the exercise from the Simulink chapters, our thermostat heating device controller, which was fully modeled in Simulink. And now let's see how we can model that in Stateflow so that you understand the differences between the modeling types, and we will also recognize which modeling style is better suited for this kind of application. As you see in the requirement, we have a lot of switch cases, a lot of conditions like if, then, else. This looks pretty much like a conditional operation, some kind of reactive system, and you can tell that Stateflow is a good choice for this kind of modeling. So let's do that in Stateflow.